Hi, everyone. We're happy to welcome you at our dynamic talks dedicated to data science. Today we'll have two tech talks, one dedicated to computer vision domain and one to latest breakthrough that moved from natural language processing to the computer vision domain. As you probably know, this tech talk was originally announced in Ukrainian. However, now we see that our audience is much broader than we expected. Because of that, we'll conduct everything in English. Hopefully, this is fine for you as well. So, Max, now I pass the word to you.
Hello, everyone. Thank you for coming. So let's start with our first presentation. It's about wallpaper replacement. So basically, we are Sevil, Smailova, and scientists at Grid Dynamics, and we would like to present you our project. So we will talk about how we can visualize your room with new walls. Next slide, please. So basically, we had a customer who wanted their customers to easily visualize how their rooms would look like with different walls. So from business perspective, it looks like this. We have a picture of our room, a picture of some texture, magic happens, and we have a new room, like our room, but with different walls. Next slide. We will give you a brief taste of what it looks like. Actually, this project is now in production, and that's what our demo looks like. So we basically select a picture of the room, select a model that we will use, select the size of texture that we will repaint, and as you can see, magically, our walls become repainted with a new texture. And now we're gonna tell you how this magic is done. So as data scientists, we had to decompose these business tasks into several data science tasks. So basically, we made we made a pipeline of different steps. So our first step would be generate a layout, generate segmentation mask, to generate walls, how we would on which we would place the texture. Then we would erase everything that is not walls and add some shades to make it look more natural. Now we're gonna go over each of the steps of a pipeline individually. So as I have mentioned, the core of our pipeline is layout and segmentation models. Layout model is basically a heat map of where lines of walls are placed. As you can see, it is a left upper picture. We need this layout in order to understand how to place textures on our walls in perspective, so it looks natural. Next piece is segmentation model. It shows us where furniture is placed, where floor is placed, and where the walls are placed. As you can see, this heat map shows us exactly where the walls are placed. So we can use it to erase everything that is not walls. As for the layout model, we used a neural network based on a paper called Physics-Inspired Optimization and Semantic Transfer Features. It was presented on CVPR in 2017 and was considered state-of-the-art, so that's why we used it. As for segmentation model, we tried different models trained on ADA20K. This is a popular dataset for image segmentation. So what this image segmentation is basically understanding where on image different objects are located. Where is furniture, where is walls, where is floor. So we finally used a model called DeepLab-ResNet pre-trained on this dataset ADA20K. And as you can see, we have pretty good results. And next, my colleague Sevil will tell you more about other parts of the pipeline. You're muted.
Thank you, Max. In order to present to a user our tiles, our texture as a tiles, we have to rescale it. And this allowed us to give a choice to a user to pick different sizes of a texture and of the tiles. At this step, we have a resized texture. We have output of our layout model, and we have output of our segmentation model. Next, what we did is we estimated our planes of walls, and then using homography projection, projected our textures onto walls. What is left is to erase furniture and other objects from the wall. And in the end, we will receive this picture. And in order to make our final picture to look more naturally, we have to transfer our shades from our old picture of a room to our new picture. And we used it using the HSV representation of the picture, where we use the last channel, V channel, that is responsible for the blackness of the picture. And we played with it in order to transfer these shades to our new image of a room. So the problem here occurred where some walls have a lot of patterns on it. For example, a lot of black patterns. For example, these black stripes are problematic because they also was in the last channel of the HSV representation. And when we transferred our shades from the original image, we also transferred these stripes, black stripes. And in order to transfer only shades, we played with different algorithms, tried to transfer per some thresholds, or maybe do some clusterization. But in the end, we just decided not to transfer shades onto the wall where there are a lot of patterns, a lot of stripes, a lot of black patterns here. So we have our pipeline, but it works too slow for the user. It takes from 40 seconds to 2 minutes to produce the final picture. And what we did in order to increase our inference time is that we cached the output of our 2 neural networks. We also resized input image of the room if it was too big. And we ran our pipeline using GPUs. And here we always have this compromise between quality and speed trade-off. Our first iteration and our first pipeline took up to 2 minutes, but obviously with a higher resolution of input pictures, you will have a better segmentation. But when we reduced our input images and did these all manipulations with caching and GPU utilizations, we reduced our inference time up to 2 seconds with some reductions in the quality, but it will be just fine for our use case. And so here you can see which parts of the pipeline were cached. These are 2 outputs of our 2 neural networks. We end up with 3 services, and we deploy them on AWS. We also added later some improvements. We added such options as a floor or ceiling, when user can choose to redesign his floor and ceilings. We tried also some last of the SOTA models like BAT model, and we also improved some shades and lighting transfer. Here I want to show you some examples how a model work. Yeah, let's start with this picture. And here you can see the out. Yeah, and also we compared our model with the existing production service, and here you can see how our model and the production one works. Another production one. This is a good picture in order to check how the models work with lighting and brightness and shades. And here you can see that our model works fine with it. It was successful to transfer the lights from the window, also the shades. But the one that we compared our results with didn't do this. This is a problematic example of a wall with the black stripes. And here you can see that our pipeline managed to replace this and to segment this wall and replace the textures, while the other one didn't manage to understand whether it was a wall or something else. Thank you for your attention, and we would be happy to answer questions if any. That silence.
Okay, so we also wanted to emphasize that this project may look simple from the first sight, but actually it included a lot of research and development tasks to find the proper solutions for each step of the pipeline. And although it started as a small POC, it successfully made it to production.
Yes, that was an awesome project we worked with, and yeah, it was a pleasure to do such things. If we don't have questions,
someone has a question.
Okay.
Yeah, I have a question. I saw in the picture you say you used Docker on AWS. Why you didn't use Lambda function from Amazon, for example? Thank you.
Actually, Lambda functions are limited into resources that and size of images or functions that can be handled by them. And unfortunately, we exceeded these limits at some point of the pipeline, so it wasn't an option for us. Yeah, sorry for interrupting, Sevil.
No, thank you for an answer.
Thank you.
Any other questions? Don't hesitate to unmute and ask if you have any.
I have another question. How long your model is trained?
We didn't train models ourselves. We used the pre-trained ones to combine them. We used the first layout model that was pre-trained, and segmentation also, the developed one. I can go. Back. This was the layout model pre-trained, and we tried to pick one of the segmentation model. Some of them were trained on the COCO, some of them were trained on the AD20K, and the ones that were trained on this dataset. This dataset is basically comprises the images of scenes, different interiors or outside roads, and it seems that they showed the better results, and that's why we used it.
Thank you.
Okay, thank you to our speakers. If we don't have any other questions, let's move to the second topic. Our second topic will be presented by Andrii, who is also a data scientist in grid dynamics. So Andrii, please start.
Yeah, okay. Do you hear me?
Yes, we can hear you well.
Okay. Okay, let's start our presentation. Let's start our presentation, NLP in computer vision. It will be a quick run. I will present and Oleg Lukyanikhin will help me. For this presentation, you should have some preliminaries. For example, you should be familiar with transformer architecture. So let's go. Today, we are going to discuss a few architectures. The names you can see: Imagerpt, Vision Transformer, Swing, Data, and so on. Also, we will I hope we will have time to look at Lambda Networks, Involution, and MVIT, Multiscale Visual Transformer. Okay. So let's start. Let's record transformer architecture in general. From the paper, attention is all you need. So you should be familiar with all that stuff to understand all the next points, because it will be a quick run through the architecture. So what we have here, on the left, we have encoder, on the right, we have decoder. And this is for machine translation task. This attention mechanism is better than RNN because we can implement all calculation in parallel, but it takes complexity and square, and is the length of sequence. And why it's arise? Please look here at the scaled product attention. We have our input, like our two-dimensional matrix. You can see here on the left bottom. We have embeddings for our words. We have our two-dimensional matrix X here, and we pass it through linear transformation to get queries, keys, and values. So when we have these values embedding, let's concentrate on it. For now, we have it not context-aware embeddings. We need, because each vector stays the same in any context. Each word will have the same embedding. So what we have to do, we want to make this representation for each vector context dependent. For that, we need weight all the words in the sequence and just sum all the stuff. The question is how to get this weight. For this, we have queries and keys. We just multiply them and make softmax operation. Here you can see formulas below. And after that, we will have weights for our values matrix. And we can perform this weighted sum of factors, and now they will be content dependent. Also, it is important to have this positional information. For this, we'll have positional embeddings. Here we have formulas. Position is like the number of words in the sequence, and I here, it's like dimension in our embedding vector. So, and here on the right, you can see how all the calculation is done on the simple example. Okay, let's move. And here, the general architecture. You can see here, we have our original matrix with words and its embeddings. We pass through multiple head attentions. Then we concatenate this outputs of head attentions and multiply it by our final matrix to obtain our original dimension as input. And then we have skip connection here. And also we have feed-forward network and again skip connection. It is just one encoder block. And in the decoder stuff, you can see that now keys and values is like encoder representation of our English sequence. Keys and values came from encoder part. And as input, we have another language, and we try to predict the next word in this sequence. Okay. Now Oleg will discuss few architecture. Please, Oleg.
Okay, thank you, Andrii. So why do we care about this? We actually, so why do we care about this? Actually, transformer architecture made a breakthrough in natural language processing. Attention mechanism allowed us to receive context-aware embeddings and afterward solve the problem of training on a huge data sets for text. This had an influence compared to the convolutional neural networks did in computer vision domain. So after a breakthrough in natural language processing, naturally, some people tried to transfer this knowledge, this architecture to some other domains. And today we'll consider architectures that successfully utilize attention mechanism and some parts or purely transformer architecture to solve computer vision tasks. And we'll start with vision transformer and Imagerpt. These two are the most straightforward way to apply transformer architecture in the vision domain. So transformer operates with tokens that are one-dimensional. Images are at least two-dimensional, and this is a problem. How can one solve it? Obviously, the most straightforward approach is just splitting your image in some patches and then flattening them. Authors of Vision Transformer did exactly this. There are some minor tricks to make it work properly. For example, patches are flattened not by vanilla reshaping, but with a linear projection. Basically, this matrix is learned during training process, but still the idea is quite straightforward. Yeah, for sure, when we say that something is straightforward or simple, we don't want to underestimate the contribution of authors, but rather want to emphasize that this isn't rocket science and these ideas are quite easy to understand on the high level. So when you split your image into patches, in this case 16 by 16 pixels, and then unroll them with linear projection, you can just pass them inside the transformer and have some results. Basically, that's it. Sounds quite simple, but this results beats vanilla CNN architectures in almost all classification tasks. At the moment of publishing, Vision Transformer occupied top 1 place on almost all leaderboards for benchmarks in vision domain. Yeah, next slide, please. Another model that uses almost the same approach is Imagerpt. Let's consider it in more details to find what is the difference. So again, Imagerpt is a transformer, namely GPT-2, that uses the same approach. You split image into patches. You can choose the size of the patch, but it's not the main idea of this approach. So you split image into patches, flatten them with a linear projection, and then use GPT-2 as a command transformer, and basically the same way you use it in natural language processing domain. What is interesting about this model? One trick is that authors reduced dimensionality of these tokens by going from 24 bits color palette, that is basically RGB color space, to their own 9-bit color palette that they come up with and optimize to use in this application. It wasn't top 1 result in the benchmarks. It just showed some comparable performance to other convolutional neural networks that were playing in the benchmark. However, next slide, please. However, there is one important thing this model introduces. It has a pre-training step when we consume visual information in an unsupervised manner. Basically, ImageGPT has 2 learning objectives: autoregressive, that is predicting next pixel, and BERT-like learning objective when we are trying to predict masked pixels from their context. This worked like a charm. By having this pre-trained, let's say, language model for pixels, the model is able not only show comparable to state-of-the-art results in image classification, it is also out of box is capable of restoring images. And you can see an example below at the bottom of the slide. So we have a partially occluded image of a cat, and all these results are produced by a model, except the most right one. The most right one is ground truth. And as you can see, all of them are meaningful. There are some minor strange details at the third picture, but all of them are great as for the generation or restoration of such a big occluded part. The great thing about this paper that inspired me the most, authors claimed that they didn't cherry pick any results. So please check the original paper if you are interested. Yeah, obviously there are more complicated architectures that are beating the simple approaches in the benchmarks, and Andrii will tell you about them.
Yes, thank you, Oleg. Let's continue to discuss next architectures. And the next architecture is Swing Transformer. Yeah, it is one of them that I recommend to read because it is state of the art in a lot of tasks. So let's look at that architecture. Here at the bottom, you can see that we have image and we have three RGB channels. And we have patch size 4 by 4 by 3, and we have 48, yes. And we have H, it's like height, and VW, it's width of image. It's height divided by 4 multiplied by width divided by 4. It is the number of words, and each word has dimension 48. And then we project this 48 with this linear embedding layer. We project this to the C. It's our hyperparameter. We can choose this C. And after that, we have swing transformer block, consecutive. On the first stage. On the second stage, we have this patch merging. What is help us? We just combine two words by embedding dimension. So number of words decrease and the embedding dimension increase, and so on, so on. This patch merging is on each stage. And you can see that swing transformer blocks, they they are multiple of 2 because they are going in the pair. So on the right, you can see that we have 2 consecutive swing transformer blocks. So basically, it is just original transformer encoder block. Yes, but here we have WMSA. It's windowed multi-head self-attention. What is windowed? It's mean like in long former architecture or in Big Bird architecture from NLP, when we reduce the number of tokens we can attend to. Because if we attend to, if our sequence is very long, it is not computationally efficient to attend to all tokens one-to-one. Yes, so we just restrict us to some window for tokens. And this is first block. And the second block is SW. It is a shifted window. It is the additional findings, and we will discuss it on the next slide. But for now, we should see that from original NLP transformer, this architecture is slightly different because layer normalization is at the beginning, not in the skip connection point. So this is the difference for computer vision transformer blocks. Okay, so let's discuss the sliding window. Here you can see layer 1 and the layer 1 plus 1. It's layer L and layer L plus 1 should be. So it is 2 consecutive layers. And we can see red window, and we can see this gray squares. It is patches, and in each patch could attend to another patch inside this window. In the first layer, yeah. And the second block, we have shifted window. We can see that this window is shifted, of course, and what it helps. For example, if you take third patch in the layer is the first layer, it can attend only inside this window. But in the next window, this third patch could attend to the window much more wider points on the image. And this is a beneficial part. Below you can see ablation study when we without shifting window and with shifting window. For image classification, it is not very important shifted or not, but basically, yeah, we can see that 1 person is added to the top 1 accuracy on ImageNet. On the detection COCO data set, on the object detection task, it's very important, shifted windows. And of course, for image segmentation, it is also important. So swing transformer, for now, is the state of the art. In the end, I will show you a table with state of the art models in different domains, on different data sets. Okay, that's all. Okay, on the right, you can see that comparison between swing transformer and visual transformer. When we have visual transformer, we have just patch 16 by 16. And in swing transformer, we have different scales of our patches, 4 by 4 pixels at the start, and then 16 by 16 at the end. Okay, now let's discuss how to use transformers in object detection. This is a data architecture. By the way, here you can see links below. So if you want to read the paper, you can go there. Okay. So the data detection transformer is very simple. It uses backbone. Basically, it is so simple that this is the code. All the stuff is here. So it just use regular transformer architecture with encoder and decoder part. What is tricky is here, you can see that it used backbone. It's ResNet. Let's look here. It should be backbone. Here you can see backbone is ResNet 50, or could be something else. It's not important. So it used feature from ResNet, add to those feature positional encodings, again flatten all the stuff, and pass to the transformer encoder. But what is our, in the transformer decoder, what is our queries here? It is some embedding learned vectors that help us to figure out where is object located. So, for example, this green token could be something like some class object, yeah. And if we need, for example, to figure out which object we have, we can pass here 100 object or just 2 queries and get whether we have those objects on the image. It is like very interesting stuff. And what is also interesting with that we can also implement panoptic segmentation. For example, we have image with age and width resolution, yes, but our final segmentation picture will have a slightly lower resolution. It's like height divided by 4 and width divided by 4. Yeah, and it's also possible to implement it with transformers. Okay, let's go next. This Vertex architecture, it is very interesting architecture because it helps us to learn some visual features from text. So the model is also very simple. We have image, we have some visual backbone. We got some features with 7 by 7 by 2048 dimensions. Then we make linear projection, and we got 7 by 7 by h. H is our hidden dimension. It's like word embedding dimension and so on. So we have 49 words by h dimension. Yeah, and we pass just through one layer, with backward transformer. What is backward transformer is learning? It's start, you can see apples at looking. Yes, apples at looking. It goes backward in our caption. And another transformer, we have forward transformer that looks brown and while purple and so on. So it look in forward direction for our caption. And we just train after regressively this model to predict the next word in each of this transformer, and we can train our visual backbone having these captions. So what it helps? It makes classification learning data efficient. You can see here. Let's look at the blue line. It is like Vertex 5 captions when we have 5 captions for image, and for the green line, it is our ImageNet supervised trained model. And you can see that having much more less data, number of images, we can got better metrics. But of course, on the right, you can see if we continue train our ImageNet supervised model, with time it will get better and better results. But if we want better results with limited number of images, we can implement this Vertex architecture. And what is also cool stuff, we can take this backbone, set up another head, and we can make object detection. So paper claims that visual feature from Vertex are more data efficient. But of course it is discussable, but okay, let's believe them. Okay, and this is maybe a lot of hype in the internet. It's image generation architecture, image generation from text. And let's discuss this architecture because there are a lot of some details in that architectures. Basically, the architecture is just simple autoregressive transformer, the decoder part. That's all. The main findings is what to feed to this decoder part of transformer. And this is the first stage. They train discrete variational autoencoder to compress images with resolution 256 by 256 into image by 32 by 32. And now we have, for RGB, we have like 24 bits of 24 bits for color resolution. But now we have, as it is discrete variational autoencoder, we have only possible near 8,000 values. And this is cool stuff. And what they concatenate first, we have caption. We have caption for our image, and we take 256 tokens from the caption, and this and the vocabulary size is like 16,000. And we take this 32 by 32, just flatten it. So, and what we have 256 token with textual information and 1024 tokens with image information, and they just train it. And now when we will have some new textual information, because we have GPT, we will ask it to predict what is the next token. And the next token is by nature is image token. That's how the model works. And on the left side, you can see that we have, for example, some text information, and we have some image points. So we have text tokens, some image tokens, and we can continue image tokens with that. So this is also cool stuff with this architecture. And here, as on the image generation task on the MS Coco data set, you can see that GAN architecture are first places. But inception score, it is the score how to estimate the quality of generation. With some blur kernels, DALL-E is better. In the publications that claim that they estimate by humans their performance, it is better, but okay, it's understandable. And one trick detailed here is they used a different attention mask in their layers, because you can see here that we have first tokens are attended always, because these first tokens are text tokens. And here, for example, we have image token could attend like only inside window, not to the whole picture, but inside some window region. Yeah. And you can see that model is very huge, basically 12 billion parameters and trained on 250 million images. Okay, so the next approach is like unsupervised approach named Dino. What it helps us. For example, if you have unlabeled images, you can see here bottom up, you have unlabeled images, but you want quickly generate some attention over the pixels. And it can help you to make like segmentation without ground truth. How it works? This architecture, it is basically very simple. You can see this algorithm is here. The main logic of the working. We have some image. We crop the image, and for example, if we have and we pass one augmented image to the student, another to the teacher. And the student and the teacher, they should coordinate some features. They should predict the same features here, but student can see just one part of the picture and teacher could see another part of the picture. So the common part of the picture will be attended, should be attended by student and by the teacher. And that's why they can learn. So without any labels and segmentation masks, we can get such very pretty attentions to the picture. Okay, the next is a clip approach. It is also very interesting stuff because we just encode text. For each text we got some vector representation, and for each image we can got some representation. And after that we just make inner product of those vectors and got such metrics. And we can train our text encoder and image decoder. On the right, you can see how to do that. We just need a cross entropy loss from different axes for each of them. And what it helps us. For example, if we have some image, we got image features, and we want to know which object is on the picture, and we can make a different. We can try different words. For example, plane, dog, car, bird. Any of them got factors and just make inner product, and the highest value will show us which object is on the pictures. And with this approach, you can see on the right different data sets how they perform better comparing with ResNet. Okay, long-short transformer. It is maybe very hard to understand, to catch all matrix manipulation, but basically here is two ideas. It is here we have just short-term memory, short-term attention, and long-term attention. Short-term attention is like long-former or big bird. It's like windowed attention. It's like windowed attention, but long-term attention, why we need long-term attention, it means we should take into account all tokens, but it is very cost operation. So to reduce the cost, we just make linear projection with keys and values. It is very similar like linformer, but in linformer, we reduce the dimension of keys and values, embedding dimension of keys and values. And here we reduce the sequence length. And after that, we just concatenate our long-term and short-term matrices, and it is our output here. As you can see here, this long-short transformer, it shows some better results on text and Wikitext data sets compared with transformer, but it is not anti-reformer and so on, but it is not a very huge difference as for me. What is much more interesting here, that when we have bit per character metric, transformer long short has 2 times less parameters to achieve the same results like a compressive model, and it is a good result. On the image classification, this transformer, long short transformer, they also tested in the publication how it performs on image. It comparable results, even better compared to date and ResNet. Here on the left, you can see. So let's go next. The next is very interesting model is transformer Unet. So if you're familiar with Unet, it's like a state-of-the-art model for a lot of segmentation tasks, but they just in the publication, it's ordinal Unet, but they add here after CNN, they added transformer layers. And that's all. And then pass those features to the upward pipeline. And if you see, and what they get state of the art on the medical data sets. So you can see here ground truth labels on the medical data set, and transformer Unet, and ordinal Unet here on the right. And maybe it is cherry-picked examples, but visually we can see that it is better. Just adding transformers to ordinal Unet, and you get better results. And you can see here that previous DICE score was, I suppose, 75, 76, and they get 77. And also they reduce it house door distance. Yeah, so just adding transformers to at some point to the architecture, and that works. Okay, the next transformer architecture is a data efficient image transformer. It is just a regular transformer, but with a distillation token. They add as teacher here, they used convolutional neural network. And what is interesting here, they use as teacher convolutional neural networks with 84 million parameters, and it best results is like 82 on top 1 accuracy on ImageNet. But then they train in their pipeline this data efficient image transformer, and they got something like 85. So this is the cool stuff. What it means? So it means that when we train transformer, it is some another nature of attention, and this teacher that learns from convolutional neural networks gives some additional information to our transformer, and it can beat state of the art. You can see comparison with efficient net and so on, and the computation cost is less. So that data efficient image transformer is a very interesting approach. And not very known approach is Lambda Networks. Let's talk about Lambda Networks. Lambda Networks are, it is not, here we have a classical attention approach. The Lambda layer transforms each context into linear function lambda, that is applied to the corresponding query. So what it means that we take some context and transform this context to Lambda function. And after that, this Lambda function is applied to query. It is not classical attention, but it was inspired by attention approach. So, and here, how it works. We have some context. For example, we have M tokens with dimension D. This M tokens is like the number of patches. Yep, and we make from that keys and values. Then we make this is softmax here with along dimension M. And after that, we calculate lambda function, lambda C, it's lambda context. Also here we have this E1, En, it's like positional embeddings. And we have lambda positional. We add those lambdas and we got our lambda. And you can see we have n lambdas, and we have here we have n inputs and inputs from our image. And now this lambda matrix applied to each of these our queries. So it is different approach than standard attention mechanism. And what they got here? They got here you can see inference time. The economy of parameters. It is less than efficient net. Yep, and results are comparable here. Another inspired another derivative from maybe from attention or maybe even convolution is involution. It's something named RedNet. If convolution convolve, for example, some window, yeah, and all the stuff, this is works another. This take just one pixel. We have width and height and channels. Take one pixel. Function phi make this pixel to the form key square. Then we unrolled this key square, and after that we apply this matrix key by key to all the channels by sequence, and we got key by key by channels. And after that, we just sum up all the stuff and got only one. So it's look like we from one pixel we derive the information about all other pixels around, and then just reduce the dimensionality of all the stuff. So this is not convolution, this is involution, because we go from one pixel to all other pixels and then again contract to one dimension to that pixel. So what authors claims that they improve performance of ResNet 50 by some percent, you can see here, but it is just interesting stuff about this. It need for check. So, and the last architecture for today is, it is a multi-scale visual transformer. Multi-scale visual transformer, it was originally, if you can see on the output size, we have height, width, and we have our dimension and T. It was for video information, but basically we can delete this T dimension times temporal dimension and work just with ordinal pictures. And here we have pull attention mechanism. Pull attention mechanism, it is slightly different than original attention, and it works. Basically what they achieves, good results for Kinetic 600. It's like working with videos. And on the ImageNet, yeah, they also declare the improvements. Let's compare here. Okay, so multi-scale visual transformer. Because I haven't a lot of time to for now to discuss all the stuff what is going on, but it is just a trick with contraction with a number of words. Yeah, in the original attention mechanism. Okay, let's go. So what we have, the conclusion for now, if you look at the state-of-the-art models, we can see that for ImageNet classification, we can see first place is CoAtNet. CoAtNet is convolutional with attention, but second place is a poor visual transformer. It's huge visual transformer, but basically it is less parameters have than this CoAtNet. When we have segmentation, it is one word, swing transformer, shifted window transformer. You can see COCO instance segmentation, swing transformer, COCO object detection, swing transformer. Okay, and ADA 20K semantic segmentation, and so on. On the CFAR classification, efficient net still state of the art. And in the image generation, GAN architectures are working, but I suppose we will see some publications that will, by like Inception Score, yeah, we'll see some publication with transformer architecture, and text to image generation also will be will be with transformer on the top. Yep, and thank you. Maybe you have some question. Okay, no questions. We can stop, or someone have.
One short question from my side. Which of these architectures you would suggest considering first? I mean, if I have time only for reading 2 or 3 papers, what should I consider first?
Yeah, my recommendation it is shifted window transformer, swing transformer, of course. Swing transformer, it's of course depends on the task we have. One moment. Swing transformer, I recommend, and Lambda Networks. It is very interesting stuff because so 2 publications, swing transformer and Lambda Networks.
Thank you.
Okay, I can see in chat. So maybe some questions, or we can end up a meeting. Yeah. Okay, have a good time, because we have some from different time zones. So maybe a few words from your side, Oleg, because. Oh yeah, thank you, Oleg, for preparation. He helped me a lot of with preparation of this presentation, and I think that's all.
Yes, thank you everyone for attention. We're happy to have such audience. Don't hesitate to contact us later if you have any other questions.